In this module, we're going to discuss some of the terminology and formalisms that are used throughout this course. There are certain words that are necessary to understand. There are certain mathematical concepts that we also need to use properly. And at the same time, I'm going to be presenting a rather informal treatment of a very formal subject matter. And the reason I'm doing so is because even computer scientists use these terms in a rather informal way when discussing the behavior of an algorithm. And so I think if you're interested in the subject matter, by all means, dive on in and find more stuff in this area. But I'm just going to give you just enough that you can use to talk with peers about the material, but also to be able to read documentation where programs refer to the performance of their algorithms using these terminologies that I will introduce now. What is an algorithm? It's fundamental to understanding this entire course, and it's fundamental to computer science. The one I'm going to use for today is this idea that an algorithm describes specific computational steps to compute an exact answer for a single problem instance on a sequential deterministic computer. Now, that's a mouthful, but I'm trying to capture certain key concepts to make sure that we're on the same page. The first notion is deterministic. We're looking for algorithms which are programs that will produce an answer and it will give me the exact same answer every time I run the program when given the exact same input. I'm going to use the idea that we're using a sequential computer because there's been such massive advancements in computer hardware with multi-core and parallelism that we really fundamentally have to approach our algorithms from a different point of view when you know in advance you have parallelism at your availability. So this fundamental structure is a deterministic sequential computer, and I need to then understand what are my steps for computing a certain task. Early on in computer science, they realized that it didn't matter what language you used to program. There were certain fundamental issues about describing an algorithm that you could do without worrying about the actual nature of the programming language that you used. And this actually made it easier to compare two different algorithms because you didn't have to worry about the language used or who wrote the program. You can instead focus on the specific steps and the data structures used by those algorithms. So we want to focus on the behavior that's inherent in the algorithm, abstracting away all the arbitrary issues that arise when you talk about a particular programming language that you use, even a particular version of a programming language like Python. What platform that you're using, what's the computer chip speed, what's the cache on the chip. There's so many issues that can improve or make your performance worse, but from the point of view of a computer scientist, the algorithm itself has a certain inherent behavior. And in the long run, the particular behavioral differences about what platform you're using or what language that you use, in the long run, they don't matter. So we need to understand the concept known as asymptotic analysis. It's a mathematical term that basically says, as you work on problems that are of increasing size, getting larger and larger, tending to infinity, but of course never getting to infinity, you need to be able to characterize how a function behaves, how an algorithm behaves. And we're going to do that using two measures. The one that is dominating the discussion is time complexity. It's to focus on the performance. How does the algorithm perform on a particular problem instance of size n? And I've already demonstrated this in some of the earlier examples. When I want to look for an element in a list or in a collection, I concern myself with the size of the collection. When it gets twice as large, that's how I can determine the behavior of the algorithm, how the program behaves when the input size doubles. And what I really want to do is come up with some shorthand mechanism to be able to characterize that. And we have to use functions to do so because they capture the quantitative analysis that we're looking for. So when I call time complexity the analysis that we're working on, I'm trying to compute a function t of n. And that would relate the number of computational steps that I need to solve a problem to the problem instance size n. A secondary measure that is also important, it's something that we can't ignore, but is always in many situations a secondary concern, is what is the space complexity of the algorithm. Clearly there's an input problem that contains input to be processed, but maybe the algorithm requires additional space, temporary storage on which to work. And when I compute the space complexity of an algorithm, I will use the term S of n to relate the size of the extra storage needed back to the size of the input problem n. And the cost model that we use to determine the behavior of the performance of an algorithm has some very simple characteristics. We start by assuming that there's a constant cost to every operation. If I have to add two numbers, it doesn't matter whether those numbers are 2 digits long or 100 digits long. I'm going to assign that as a constant cost. I'll assume that dividing or addition or subtraction, they're all the same cost. Now we also understand, in practical terms, on an actual hardware platform, a computer chip performs faster with addition than it does maybe with floating point divide. And those concerns in the algorithmic space, I'm trying to ignore when I'm just trying to understand the complexity of the algorithm from the point of view of the steps that it carries out. And on a sequential deterministic computing platform, you can determine the exact total number of operations, basic operations, that you need to perform, and you can tie it back directly to the size of the problem instance. So let's get started with a small example. I can't think of anything smaller than trying to sum the numbers in a collection. If I wanted to compute this in Python, I would just write a small for loop that adds all the numbers together, producing a sum. In the algorithms that we analyze, it doesn't matter, or it shouldn't matter, whether the data is stored in a file, if I have it in a linked list, if it's stored in a string, and I have to somehow find it amongst all the commas. Those are all arbitrary decisions about the representation of the problem instance. Some are more efficient than others, but the underlying algorithm is itself fundamentally the same in each case. And this algorithm needs n operations to add the elements together. And so the time complexity of the algorithm, T of n, we would say is directly proportional to the size of the elements that are being added. If I have 1,000 elements, it will take a certain amount of time to compute that. If I suddenly have 2,000 elements, one would expect that the time is now going to be twice as much. And that's what is meant by directly proportional. And what I'm really concerned about in algorithms is to understand what's called the asymptotic growth. How does the problem behave as the problem instances get larger and larger? And the reason we do this is there's a fundamental problem that's known in mathematics as the law of small numbers. Things that seem to apply with small data sets somehow don't apply when you scale it up to hundreds of thousands. And the only real measure of understanding the behavior of an algorithm is to really understand what happens when you have several 100,000 or millions of elements in your collection of your problem instance that you're working on. And so that's a true measure. And so what I'm really trying to determine is this concept called the order of growth. And this is what is known in computer science as the big O notation. And there's a formal treatment you can find in any textbook or online as you wish. And you can definitely find more details there, and I encourage you to do so if you're interested. In this module, I'll be presenting a rather informal treatment, as I've said, that's suitable for industry, and indeed is suitable when you're talking to computer scientists who often fall back on this shorthand when describing the behavior of their own algorithms. Let's look at the execution time of sum. I ran it on Python. I might do that later, but it's not important. You can understand how it would work. And when I run sum, I quickly develop a small graph that shows on the x-axis the problem size as it grows, 20,000, 40, 60,000, and so on. On the y-axis, the time it takes to perform that computation. If you perform this and then generate the numbers and bring them into Excel, you can very quickly identify a straight linear relationship between the size of the problem instance and the amount of time it takes to compute. And I think we would all agree, it doesn't matter what programming language you use, as long as you're on a sequential deterministic computer, you can end up with a similar line. It would in fact be a line. The slope of the line will change depending upon the programming language used, the chip speed, and other factors that are really incidental when it comes to understanding the behavior of the algorithm. And so we would say that the sum program that we just described exhibits linear behavior. As the size of the program instance changes and increases, the size of the performance in execution time increases. And in shorthand, or using the formal definition, we would say that it's order n, or big O of n. And that is a fundamental question for every algorithm. What is the order of its growth as the problem size changes. And what we really want to do is come up with a single value. It doesn't matter whether we look at a value, the problem size of 16 elements, or 32, or 1024. We want to come up with a single way of referring to the behavior of the algorithm as it grows. And so to avoid this issue of small number problems, where you have some really great code that works as long as you only have 10 elements, but once you have 100 elements, it doesn't complete in an hour or a day. In order to remove all those considerations, the big O notation has the following formalism. It assumes that you will work your algorithm on increasing size problems n, and that will change depending on the nature of the problem. In a binary array search, it would be the number of elements in the search. In a binary search tree, it would be the number of elements in the binary tree. All that we are concerned with in this analysis of asymptotic growth is that as the size of the problem size n increases, and we say mathematically for sufficiently large values of n, if I want to determine that I have linear growth, in this case I know I do for my sum algorithm, I would say that the order of growth is linear, which means that as n gets larger and larger, there will be some constant c, and I may never actually need to determine what that constant c is. There will be some constant c that will determine the maximum number of operations that you need to perform for that computation on a problem instance of size n. So to go back to that earlier slide with the graph, you will see that the slope of that line determines the growth rate of that algorithm. Now the slope of the line could be different depending on the implementation and the hardware that you happen to use, but it will always exhibit linear growth on a deterministic sequential computer. And I don't need to know what C is, I just know that it exists. And when I plot my execution times, I will see that direct correlation between the size of the problem instance and the behavior time. And so what really matters is the observation that T of n is represented by the function n. It's exhibiting linear growth. And if I wanted to write some code to demonstrate this, and you can look at the code after the video, I would run a number of trials. And here I'm generating a bunch of digits, in this case, random numbers from 1 to 9. And I want to randomly add those together, starting with 2 to the 16, then 2 to the 17, 2 to the 18, and so on. A very large number of runs. And when I do this, I create a scores for each one that keeps track of the time that it took to sum up those numbers. And at the end of it, I produce the chart that you just saw earlier. Now, this case here, I've chosen a very specific problem, adding 2 to the n random digits. And n, in this case, is going to be the size of the elements, which is going to range from 2 all the way up to 2 to the 16. As I've already demonstrated, that exhibits linear growth, or order n. I'm just going to make a small change to this algorithm. And now consider, what if I generate 2 to the n random digits, and now I want to sort them using Python's built-in sort mechanism for any list. So it's not clear what the performance expectation is. I have to run it to get a sense of what it would look like. When you do this, you'll see some interesting behavior. I'll first show you the overall chart, and then we'll go back and look at the code to see what it looks like. On this graph, I've got 3 different lines. The first line is the one that sums n random digits. That's the adding 1 purple line all the way at the bottom. As you see, it exhibits linear growth. But then I have 2 other lines. The one in yellow is when I'm sorting n digits. So I may have 1,000,000 digits, but the numbers are only numbers 1 through 9. The blue line is when I sort n random numbers that are in the range 1 to 2 to the n. So it might seem odd. The first thought is that, well, why is there a difference of behavior? Why does the yellow line look like it's very close to the purple line? In fact, I'm wondering, is it linear? And why does the blue not look linear at all? In fact, as you look at it, it looks like it's curving up slightly. It looks like it's accelerating. And so I don't know how to characterize its behavior. Now, to really witness this in action, let's go to the code so we can see what the code looks like. I now have 2 functions that I've coded up. One to compute the performance of sum, and the other one to compute the performance of sort. As you can see, I generate a number of trials, and for each one I create a random list of digits from numbers 1 through 9. And I create a total of 2 to the n of them. The first function will just sort will sum them all one at a time, compute the difference in the time, and then keep track of that in a scores dictionary, which I will then print up at the end. When you run this function, as you will see, as the size of the problem size doubles, the time that it takes to perform those computations will also double. They start off very small, but as you can see toward the end, 0.1, then 0.2, and 0.4, and so on. So if I look at this and I recognize that the problem instance is doubling in size and the time it takes to complete the performance is also doubling in size, that tells me that it's exhibiting linear growth. The time to compute is directly proportional to the size of the problem set. A slightly different variation over here, the performance sort. Let me run this one. I'm going to run on a smaller set just so I can fit it on one screen here. And if you look at this, it looks like it exhibits the exact same behavior. It looks like as the problem size doubles in time, the performance time also doubles. So you would look at that and say, I wonder, is the sorting algorithm, does that exhibit linear growth? And the thing that is surprising here is I'm going to make a small little change. I'm not going to sort just random digits from 1 to 9. I'm going to sort a bunch of random numbers. And those random numbers will be drawn from this larger set. Not just 1 to 9, but 1 up until 2 to the size. And when I generate this, that small little change, you could look at that and say, well, my problem size, the time it takes to complete, is noticeably bigger. It's almost twice as large, again, as it was before. And you would wonder, well, what happened? I didn't change the problem. All I changed was my input set. So this notion about an algorithm is that its behavior is very sensitive to the size of the input set, but also the quality of the input set. And if you reflect a minute on what the earlier problem was, I was sorting a bunch of random digits, 1 through 9, and I might have had 1 million of these. So clearly there's a lot of duplications in that set. And somehow being able to sort a bunch of numbers where you have a lot of duplicates is apparently a lot easier than sorting a bunch of numbers where they all are different. So as I look at this, it's unclear just by looking at the performance numbers, is this a linear growth algorithm or is there something more at work? And to further understand that, let's go back and look at the chart to understand what's really going on. These are the 3 growth curves for the 3 different algorithms we've seen. The first one in purple again is the add numbers, exhibits linear or order n growth. Sorting looks like I've got 2 different behaviors based upon not just the problem size, but the very nature of the values being sorted. So to understand what the order of growth is for the sort algorithm, I need to introduce some more functions so we can compare. This table has a lot of information on it, but it's broken down by columns, so I think it's easy to understand. On the left-hand column is the size of the problem instance n, starting at 2, 4, 8, and so on. When we did the binary array search, we observed what was called order of log n behavior performance, which basically meant as the problem size doubled, you only increased the number of steps by 1. And so if I had a phone book of 4,096 names, that would only require 1 additional step when compared to a phone book of 2,048 names. When you see linear growth, or order n, as I've just shown you for the sum, that's the second column. This is when, as the problem size increases, well, the time it takes will directly increase proportional to the size of that increase. And this is what one would expect. However, when it comes to other algorithms, you may find behaviors where the time it takes to perform is increasingly demanding. And as you can see here, these growth rates show some strange and potentially incredible growth rates. Let's look at the last one over here, which is known as the exponential growth rate. This would be when you're just trying randomly all possibilities. Even with very small number of problem instance sizes, say a problem instance size of 16, its value is already 65,536. And to get its corresponding value on the other ones, well, on the linear growth, this would say if I had a problem of size 65,536, I could solve that problem in a certain amount of time. For that same amount of time, if my algorithm had been exponential, I could only solve problems of size 16. And so what this chart shows you is a direct analog when you're concerning yourself with the size of the problem instance that you can solve in the same amount of time when the algorithms exhibit different growth. So if I have a linear growth algorithm and my problem instance is size 4096, I can solve that. However, for the exact same amount of time, if my problem exhibited what's called quadratic or order n squared growth, I could only solve a problem of size 64. What if my algorithm exhibited what's called quadratic growth? Then I could only solve problems of size instance 8 in the exact same amount of time. So this fundamentally tries to describe why we're so concerned about the behavior growth of an algorithm, because it determines the performance time as the problem instance size grows. And the ones that are ideal, naturally, are when you have log n growth or linear growth. But it turns out there's a range of other algorithmic families that are very important, and we need to understand them as well. The two that come to mind that at least we should be familiar with: order n squared growth. If you had a bunch of values in a list and you wanted to see if any value was duplicated in that list, you would have to check for each value, you'd have to compare it against n minus 1 other values. And very quickly you'd realize this is not just an order n growth. You would realize I'm actually doing n squared operations. And that means that the growth rate is order n squared. And where the other algorithms fit is based on understanding the analysis of what the code is trying to do, but also what the underlying steps that are defined in the algorithm are doing. And so to just do a quick peek looking ahead, that sorting that I mentioned before, it looked a lot like linear, but it also seemed to accelerate. And there's a certain family of algorithms that fall into this category known as order n log n. And that function, n times log n, is really a shorthand for understanding an entire class of efficient algorithms whose growth rate is determined by the size of the problem instance, but not entirely by the size of the problem instance. Whereas order n squared grows at this rather rapid rate, order n log n, as you see here, is manageable. And when we approach algorithms and we try to find solutions to problem instances that grow increasingly over time, we really want to focus our attention on trying to find order n log n algorithms, or even linear or log n. And when I classify my algorithms, I want to classify it by the order that's the closest performance. And this is what I mentioned earlier about how this is really a shorthand for what is a rather more formal treatment that you would find in textbooks in undergraduate classes in computer science. You want to select a function that has the best match. For example, you could say that sum could be described as exponential because its behavior doesn't exceed that growth rate. However, that's much too high of a ceiling because you can clearly do it in order n. And so you want to find the family of algorithm of functions that comes the closest to describing the behavior that you're looking for. And for this reason, we spend our time thinking about what's the best case of an algorithm, what's the average case for the algorithm, and what's the worst case. The best case are those simply that require the least work. And it has nothing to do with the algorithm per se. It really has more to do with the particular problem instance that you've given it. For example, in the contains operator, when you're just trying to check to see if an element is contained in a list, if that Python list had 10 million elements, but the target you're looking for is always the first one, that's the best case. In the worst case, you've come up with a problem instance which is devious and is the one that requires the most work. To use the contains operator again, if you're looking for a value that is not in the list, well, that's the worst case, because you have to go through the entire list to make sure that it's there or not there. And after just understanding the worst case analysis, it's worthwhile trying to consider what's the average case that you're likely to see in practice, because the vast majority of remaining problem instances fall into this category. And so if I were sorting n numbers, which is an example that we'll use, the best case is that they're already sorted and I don't have any work to do. In the worst case, there are many different ways of looking at this. The one that comes to mind is, what if they're actually in reverse order? Then one would think I have to do a lot of work to bring them all back into order. The average case, well, there's a random distribution. And on those average cases, you can compute something that looks like this, which decides, you know what? On the average case, I just generated a random set of numbers and I executed the sort algorithm that Python provided for me. It doesn't look like linear growth because it starts out being small, but then it starts to accelerate away. And if you plot that and you really compare it, the growth rate of that function as compared to the growth rate of the function n times log of n, you will see that they align. And a more formal treatment would clarify that there's some constant c that exists, for which once the problem size gets over a certain threshold, you know that the time that it takes to perform that algorithm would be directly proportional to n times log of n. And the direct proportion in this case is that constant c. But we don't normally need to find what that value is. We can presume it exists because when we do this chart, we can see how it starts to taper off, and over time, or as mathematicians would say, asymptotically over time, that you achieve the actual curve of the growth rate. So I'm sorting n random numbers. The best case is when they're already sorted. And in fact, there's a special case for when there's a lot of duplicates. And so this yellow line here, which looked a little bit like linear growth, when you plot it out to much larger samples, up to 1 million, you can clearly see that it's starting to leave the linear growth rate farther and farther behind. That's what this purple line is, way down the bottom. Now the constant that's associated with that growth rate is smaller than the constant that's associated with randomly sorting a bunch of numbers. But in both cases, the behavior of the algorithm is on the order of n times log n. So you should expect that as the problem size doubles, the time it takes will more than double, but not by much. It'll just be doubling by a constant time, the doubling amount. And when I think about in this course, we're using the notation big O to clarify in a rather informal and coarse way the behavior of the algorithm as it approaches larger and larger problem sizes. We're doing so in an informal way because, after all, when programmers talk to each other, they do so as programmers and not mathematicians. But you need to understand these terms because increasingly code libraries are being documented with the performance expectation of functions. And when you see order n log n associated with a particular function, you should start to develop an intuition as to how the performance will change as the problem size doubles. Now I'll carry out 1 or 2 small examples to show how you can apply this technique when you just have a description of your pseudocode. We've already seen how the sum algorithm is order n, and it contains a simple for loop that executes over all the elements of a collection. And you can use that template as a quick way of characterizing some code you see, and in your mind you can think, oh, that's order n. But what if you have more complicated control logic? Here's an example where I have a nested for loop. And this is the problem where you have a collection and you want to see if that collection contains any duplicates. So what you have to do is, for every element in the collection, you've got to compare it against all the other elements in the collection. And if you're going to do it in a smart way, you can control it so that the first time through the loop, the outer I loop, you compare that first element against the other n-1. Then the next time through the I loop, you compare that second element against the next n-2, and so on. So the real question at hand is, how many times do you check whether 2 elements are the same? And that basic operation is executed how many times? Well, it's more than order n, because I've got that for loop, but what happens when I have a nested for loop? The way to understand this is to look at it in a small example and then see if that scales up to larger examples. If I have just 3 elements, then I'll compare the first against the second against the third, and then finally the first against the third. In all those cases then, if I have 3 elements, I only need 3 comparison operators. And that seems to be the fundamental driving force behind the performance of that code. So if n is 3, 3 times 2 divided by 2 gives me 3. So this function, n times n minus 1 over 2, is an accurate count for the number of times that that equals operator will be executed. So what is the behavior of this algorithm? What is its performance? It's clearly not order n, but how do I characterize it? Well, if I start with that function, n times n minus 1 over 2, and I break it up into its constituent parts, n squared over 2 minus n over 2. As n becomes larger and larger, the dominant factor in that is the n squared over 2. And as you start to consider larger problem sizes, you can actually ignore the n over 2 factor because it would become so much smaller in relation to the n squared factor. So this particular structure, a nested for loop, where each integer variable is being iterated from the beginning of the list to the end of the list, that particular structure would demonstrate what's called order n squared performance. The number of times that basic operation is executed is based not just on n, but n squared. So I can look at code, and as I'm casually scanning through it, if I see a for loop, I can think order n. If I see a nested for loop and I look more closely and I see that it's iterating over all the index values in that list, I can think to myself, that's order n squared. And I can call to mind those performance tables that I showed earlier that show the growth rate of order n squared, and how if the problem size doubles, it now means that it's 4 times as long to compute. And that may be the best I can hope for. But if you look at the other performance families, like the order n log n family, we were able to identify optimum performance that as the problem size doubles, the time it takes to compute the solution only doubles by a constant amount. Another way to evaluate the performance of some code is to consider how it's composed with other code in a consecutive manner. So I have a new function here called has duplicates or none. And it first has a check to see if the value none actually appears inside the list, as it can happen in Python. And if it does happen, I want to return true. Otherwise, I'm going to go ahead and compute that same duplicates check that I just showed you. So I've got these 2 sequential blocks. The first one is clearly order n. I'm just going to search through the list one at a time and find out if none is there, and if so, I'll return. So in the best case, none always exists inside the list. And in that best case, then, I would assume order n performance, because I may be able to go through and find it. However, we can't always assume the best case will happen. So if I look at this code, the first block exhibits order n behavior. The second block exhibits order n squared behavior. If I put those 2 together, I can clearly see that the order n squared behavior is the more dominant factor that will determine the behavior of the algorithm. And the order n is important, you can't ignore that, but the order n squared is much more powerful. And so when I'm classifying the algorithm, I don't just add these together, because this is an asymptotic declaration of the function as it behaves over time, is that the n squared term is much more powerful than the n term. So I would not just say, oh, it's order n squared plus n, because n is already subsumed by the n squared term. I would just clarify that by saying that whole algorithm is order n squared. And this ability to look at code from the eyes of an algorithm performance analysis, to see where the optimizations can be done to improve the performance, that's really the nature of an algorithm. When you see code that's correct but performs poorly, you want to identify where the performance hit exists, and then try to find an algorithm that helps remove that obstacle from your performance. When I consider finally the big O notation, as we've used before, let's summarize what we know so far. You've seen the order log n behavior as identified in the binary array search and the binary search tree module. As the problem size doubles, you only need a fixed number of extra steps. This is extremely efficient, and is at the heart of many algorithms. Another kind of behavior that's worth mentioning here is what's called constant time operation. And this is reflected using the shorthand big O of 1, or order 1. This reflects a fixed performance regardless of the size of the problem. So for example, if I want to see whether a list is empty or not, it doesn't matter how many elements there are on the list. It's a constant time operation. So it would be declared as order 1. You've seen order log n for the binary array search and the binary search tree. We've seen order n for that sum algorithm we talked about. This is what's known as the best polynomial efficiency, when the problem size directly correlates to the performance time that it will take. And in many ways, this is an ideal that you should achieve. Some other problems, no matter what you do, will require order n squared behavior. And in fact, this is a sobering reality, because as the problem size doubles, it takes 4 times as hard to compute the solution. And when you put this together with small problems and you get great performance, you always have to be patient, because you recognize that if you tackled a problem that was 10 times as big, it would require 100 times as much work on a sequential deterministic computer. And so the goal is always trying to find ways to solve a problem in a more efficient manner than what a naive or obvious solution would be. I've already mentioned the final column in that performance growth table, which is exponential time, or 2 to the n. Sometimes there's nothing you can do but try every possible combination. And because computers are so blindingly fast, we can actually get away with this for some pretty small number of problems. As long as n is small, say 10 or 11, maybe this is something that could still yet be used to solve problems that we have. Although you can't use it to solve problems where the problem instance is 40 or 50. That's simply too hard to require too many steps to compute. And so what it turns out is that this performance family n log n is really the sweet spot for algorithms. It's an opportunity when you find an algorithm that exhibits n squared behavior, that if you could just find the right data structure and maybe an elegant approach, you could break that problem and have it work in order n log n time instead of order n squared time. And this is not just a mathematical concern. If you have an algorithm that's order n squared, it's 100 times as hard to solve a problem that's 10 times as big. And as you know, in the age of large data, we're solving very large problems. We have to find ways to break up problems that would otherwise be order n squared and solve them in more efficient time. And order n log n is this very well-known family of approaches in computer science, where with the right data structure, you can set the problem up in such a way that the performance is not as efficient as, say, linear, but is in a really nice space that as the problem size increases, the time to complete it more or less computes directly with the small additional cost. So this introduction to big O notation by no means covers the entire spectrum of what you need to know if you're going to pursue a formal treatment of the subject. But it's good enough to be able to document your code and clarify when you have a performance hit. You're going to alert people to that in your API by saying, this function is order n squared, be wary. Or this function is order log n. It's perfectly efficient for very large problem sizes. And it's also part of the colloquial terms used when discussing performance among software engineers to quickly and rapidly identify where the real performance gains or hits are in your application. So this is the summary, completing our description of big O notation.